All right. Welcome, everyone, to another episode of Author Meets Physics. We're here with Eddy Chen of the University of California at San Diego. I'm your host, Dave Baker from the University of Michigan Philosophy Department. We're here to talk about another one of my favorite recent papers in the philosophy of physics, which is Eddy's paper, Quantum Mechanics in the Time Asymmetric Universe, on the nature of the initial quantum state. And there's been some good news about this paper recently. Eddy, it's won the Popper Prize for 2021. Congratulations.
Yes. Thank you so much,
Congratulations.
Dave. Thank you.
Yeah, it's wonderful news and very well deserved. Super interesting paper and one I'm really psyched to talk about.
Thank you so much, David. Let me also thank you for having me on this series, and I want to congratulate you on this series. Very nice interviews. I enjoyed watching the ones with Tushar, Mary, and Trevor. Recommend to any viewers also to check out those videos on Dave's YouTube channel. And very helpful to me as a junior scholar to learn about the details of the debate in a way that's deeper than just reading the paper and getting to know the in and outs of the arguments.
Yeah, thanks, Eddy. I mean, that's great. And yeah, useful remarks to preface this as well. I encourage everybody watching to read the paper, kind of to start out, or at least, take a look, skim. As always, this kind of channel is pitched at people who are professionals in philosophy of physics. The idea is to, go a bit beyond what's there on the page. And so starting with what's there on the page is a great way to kind of enter into this. Okay, so let's talk about kind of what the paper is aiming to achieve to start out with, right? So there's this classic problem. Why is there an arrow of time, right? Why does the past seem to be so different from the future? And, classically, it's been solved with various versions of this idea that Albert has labeled the past hypothesis, the idea that in the past, the entropy was much lower than it is today. And on Albert's view, that's a kind of law of nature, which is a feature that shares some kinship with the view that you develop, right? So then your goal is to kind of come up with an ontology for quantum mechanics, as I understand it, that is attractive for other reasons, but that also does work towards solving this problem. And you think that this can be done by saying that, so typically when folks try to solve the measurement problem and interpret kind of standard quantum mechanics, the move that's made is to interpret the state as if it was a wave function describing a pure state, whereas your objective is to instead treat the state as a density matrix representing a mixed state. So why don't we start out with you kind of telling the viewers more about why that move can help with these problems about thermodynamics?
Sure. Thank you, Dave. So this paper is part of a bigger project called the One Calculus. I can tell a story about why it's called the One Calculus later, but roughly speaking, the idea is that the quantum state of the universe is subjective, but it can be impure, represented by a density matrix. And I propose that it is a particular mixed state, impure state, a natural one, the most natural one given the past hypothesis, the normalized projection onto the past hypothesis subspace in the Hilbert space. I'm going to unpack that later too. But this idea gives you a unique quantum state of the universe given this postulate, this say law of nature, so that you have a unique history of the quantum state. Suppose that you obeys the von Neumann equation, unitary dynamics deterministic, and although in the GW case, you have collapses and so on. So in this density matrix picture, we have a unique microstate of the universe at T0 and unique microstate of the universe at any time that's compatible with the law. So this, I think, solves two problems. One is the arrow of time, and the other is the ontology of quantum mechanics. So the second problem first. And this relates to some of the work that, Dave, you have done on interpretation quantum mechanics. And the idea is that usually we think of the quantum state universe, if it is subjective, it must be a pure state, not representing ignorances or lack of knowledge, but something real and pure. Why pure? Well, we'll learn from textbooks, it must be a pure state, because mixed state representing reduced states, or tracing out the environmental degrees of freedom, or statistical state representing ensemble systems. And the pure state picture gave rise to several interpretational questions. What is this wave function doing in the world? It's not like a particle, and it's not like a field, and it's not like something closely related to tables and chairs, something much more ethereal, it's more mystical, it's more abstract. And mathematically speaking, it lives on a high-dimensional, vastly high-dimensional configuration space. And it's nothing like the ordinary three-dimensional, four-dimensional space-time, or maybe with extra dimensions, but it's not going to have 10 to the billions of dimensions. So this configuration space, the ontology of that is a bit troubling. One might follow, say, Albert and the suggestion that I said Bell, and say this is the fundamental space. But let's give rise to questions. Okay, if we were to live in that space, how come we have this perception of experiences ordinary objects? You're trying to solve that by saying, oh, it's functional analysis, or using all kinds of philosophical tools to bring us down to the ordinary three-dimensional space. Whereas I am very much attracted to the idea that the quantum state represents a law of nature, or something close to a law of nature. But the quantum state in the pure state case is too complicated to be a law. It is, variation in configuration space and huge variations that cannot be captured by a simple formula. You can say it is psi, but it's a kind of formal symbol. If to write out the explicit functional form, it's going to involve lots of information. So if one accepts that the initial state of universe given by the past hypothesis is very simple, and projection onto that past subspace is equivalently simple, then the density matrix compatible with the past hypothesis is simple enough to be a good candidate for a law of nature. In that case, we can say the ontology of quantum mechanics is not really about the quantum state. It's really about material stuff in physical space-time governed by a law, a simple law, a mixed state, starting in this subspace.
Yeah, good. That's super interesting. And one of the things I should say, by the way, that I've already said to you about the paper is that I love the way that the paper kind of engages with, actually grapples with, rather than, as I think some work in the philosophy of physics does, kind of making assumptions about without grappling with these questions of like, what are the theoretical virtues? What are the kind of reasons we have to believe one theory is prima facie more plausible than another as a hypothesis. So this question of simplicity, I think, is an interesting one that kind of comes up, right? So let me put the question this way. So there's a lot of kind of like disagreement in the literature on Occam's razor about what it is that we're thinking ought to be simple, right? Do we think that reality ought to contain kind of like fewer entities or fewer types of entities, or less kind of like structure that requires less information to put across, or kind of like fewer words in some privileged language to put across? So I guess the question for you here is, do you have a kind of preferred picture of what you think like the right notion of simplicity is to choose theoretical posits on the basis of?
Yeah, excellent question. Actually writing a new paper on the simplicity of physical laws to address this question exactly. And I think these are very deep, hard questions. So I have a somewhat naive picture, I think, about simplicity. I think that simplicity postulate is basic in the sense that it is not justified by further principles. And I think it's fundamental postulate we have on our, say, theory choice, or how we should conduct our scientific inquiry. So we should prefer simpler hypothesis, we should assign higher, maybe in Bayesian term, higher prior probabilities to simpler theories. And we should just confirm theories by empirical evidence, but those posterior probabilities will still favor the simpler ones over complicated ones when they're determined by evidence. So in this case, but I think that for this paper and this project, it doesn't presuppose a particular notion of simplicity. Does not presuppose a particular justification for simplicity either. It's more like continuous with the kind of theory choice principles we have in science, the ordinary ones we have, say analogous to say classical mechanics, kind of clean case theory, we have dynamical laws and Hamiltonian function, right, representing the force laws and so on. The Hamiltonian function is a good candidate for a nomological object, like a law of nature governing how things move, because it can be expanded in terms of simple function. You can write it out for Newtonian and particle system in terms of the gravitational potential and Coulomb potential and so on and so forth, and kinetic energy, and that's it. 3-4 terms, and you have the simple closed mathematical formula for the Hamiltonian function, simple enough to be a law. Whereas the wave function in the case of Bowman mechanics, for example, and similarly to some versions of many worlds and GRW, you have the wave function give rise to some kind of distribution of matter in physical spacetime. It plays a similar role to Hamiltonian function in classical mechanics, but it does not quite look like a law because in general, there's no simple formula you can write down the closed form of the psi function in terms of the variables in configuration space or other spaces. So that's this analogy I see. And that's a big problem, I think, for the nomological view of the wave function. But once you go to the density matrix picture, I think the advantage of simplicity reappears. You can say and argue that there's a natural density matrix given a past hypothesis. And if someone like Albert and Lower independently make the move that the past hypothesis represents a simple law, then the projection onto that is simple enough to be a law, giving rise to, say, how particles move, how fields behave, how density is distributed in space-time.
Yeah, interesting. Okay, so despite like you say, kind of wanting to be a bit non-committal, I think there's some very, some specific answers there that, to the kind of question I asked, right? Which is, it sounds like you're thinking of, and there may be other ways in which simplicity applies to theory of choice, but the way you're using it is as an application to something that's kind of a putative law of nature. And it sounds like the criterion is that the law should be kind of expressible in a using a simple formula that's right. Like maybe now a lot of the time folks will say expressible in a simple formula in terms of the variables that are the theory's like basic degrees of freedom. Is that the idea?
So natural properties, natural variables.
Yeah.
Okay. So it is going to be a bit language dependent. On the theory we choose, we evaluate simplicity by the natural kinds, the natural predicates that deemed natural by the theory. So if you rephrase the theory in terms of another language, that might change its simplicity or complexity. So the idea is that suppose we fix a standard of simplicity to be the standard that regards, say, the Einstein equation to be simple, regards the Hamiltonian equation to be simple, regards Hamiltonian function to be simple, then the same standard should apply to the wave function.
Good. Okay, good. So good. So that really clarifies actually part of your last answer when you were talking about using standards of simplicity that kind of come from physical practice, right? So the form of the argument you're presenting is something like premise. Hamiltonian mechanics gives an expression for a law of nature that's simple enough to be desirable as a theoretical posit. If that's true, then your density matrix formalism for quantum mechanics meets that same criterion.
Right.
And so, you're in good company, right? I like that.
Right. Yeah. Although I think in general, I don't say that it is, so I don't say a stronger claim that I think that simplicity is epistemic guide to fundamental laws. As a non-Humean, I don't say it is impossible for nature to employ complicated laws. It's just that there's no reason, or I don't assign a high probability, or no one should assign high probability to those complicated hypotheses. but it's a epistemic possibility, maybe a metaphysical one, that nature can employ even complicated laws in this world, right?
Yeah.
But in that case, we will have very hard time to find what those laws are.
Great. Yeah. I mean, you know, as you probably know, I'm in total agreement with that.
Okay.
Wonderful. All right. So now I think the next thing you wanted going to talk about was solving the error of time problem with this picture.
Right. Right. So the second problem, the first problem is this solving the error of time issue is that in the typical picture, you have the past hypothesis or something like the past hypothesis, maybe a wide curvature hypothesis, maybe quantum generalization of wide curvature hypothesis. That's a bit vague. You have partition of macro spaces, can be vague, and you have to say the initial state of the universe is in a low entropy state. How low is low? Even given the precise number of the macro variables, there is no precise correspondence with set of microstates or set of wave functions. So this is a big case problem. The other worry is that there are going to be two kinds of probabilities: the quantum kind of probabilities, the Born rule probabilities, but also the system mechanical probability over possible wave function, initial wave functions. That's in addition to the Born rule probabilities. So nature must employ two kinds of objective probabilities or chances that seems not unified in some way. It might be more desirable to have unified treatment or reduce one to the other. The density matrix picture can give a unified solution to both, I think. For the probability issue, you see that if you have a simple law selecting a particular unique initial microstate, there's no longer a need for a probability distribution over possible quantum states compatible with the past hypothesis. So there's one version that says the new density matrix is the one compatible with the past hypothesis. So the trace with the projection on density matrix equal to 1. But my version is different. My version says the initial density matrix W0 is this one, the projection onto that past subspace divided by the dimension of subspace, density matrix. So a unique one, and no longer need a probability distribution over possible interconditions. So you only have the Born rule left, or generalized Born rule given the density matrix. And the other one is that once you have a density matrix, that's the kind of extended to the entire subspace, then it becomes somewhat traceable. So we can say in the usual picture, the wave function screens off the edges of the past hypothesis. Once you pin down the wave function, the boundaries of the macro state it is in no longer matters. So for most wave functions compatible with the past hypothesis, the exact boundary doesn't matter at all to how things are in the actual world. So in some sense, there's no objective grounding or basis for the precise boundary of the past hypothesis. So you say there is a precise one, it's hidden to us. It'll be somewhat arbitrary. I call this untraceably arbitrary. There's a precise formula for why it is arbitrary, but forget about that for now. But just intuitively, the precise boundary doesn't make any difference to how the actual world is. But it's different for the density matrix picture. Suppose in the average picture, it's kind of a straightforward case, the density matrix realizes the emergent multiverse as time goes by. And the precise boundaries of the density matrix will make a difference to some branches somewhere in the multiverse. And similarly for GRW, the precise boundary of the density matrix is going to make some difference to some probabilities somewhere.
Yeah.
And for the Bowman mechanics, I think it's plausible that the precise boundary will make a difference to how particles move in the actual world. If they were different, there'll be some differences along the trajectory somewhere in space-time. So in my picture, there is a objective basis for why the subspace is this one, not this one. So it's selective precipitation in a non-projectable sense.
Now, let's see, that's interesting, Eddy. So could you say a bit more about what's so undesirable about saying that, you know, either that there isn't a precise right past hypothesis subspace, or that it's kind of, I mean, screened off by what we would ordinarily think of as the initial conditions of the quantum state. But of course, if we're talking about the quantum state as a law, you know, just that's the part of this where I have
Sorry, I went by very fast. I didn't explain very
well.
No. But the idea is this. So suppose we take the past hypothesis to be a law. So initial macro state of the low entropy universe was a law of nature that constrained possibilities.
Yeah.
And what's the problem taking that law to be a vague law? I don't think it is as bad a problem for Humeans who think of laws as part of the best system summaries of the mosaic. The mosaic can still be precise, the laws might be vague. For anti-Humeans, like me, it might be troublesome in the sense that now we have fundamental constraint law that imposes objective probability, objective modalities. Let's be fuzzy. Let's be vague. And I think there's an interesting consequence of this for both humans and non-humans, is that I think vagueness comes with high order vagueness. So vagueness of laws comes with high order vagueness of laws. That is, it is vague what the boundary is, then it's vague where its fuzziness comes from, and it's vague where the fuzziness comes from. Then this cannot be modeled by any precise mathematics. If you have any precise set theory or ranges or distributions, it's still too precise for the fuzziness, the high order fuzziness, which means there's going to be one element of fundamental physics that cannot be modeled basically by precise mathematics. So the fundamental physical theory cannot be completely and faithfully expressible in terms of mathematics built on set theory.
Good. Okay, good. Right. So as a general so the problem you're raising is that maybe the kind of ordinary pick a pick a kind of vague set of initial conditions and a wave function in that kind of approach to the past hypothesis is going to entail that it's vague what the law is, and then that kind of means that like that in a way, I mean, it's funny, right? In a way, like the effectiveness of mathematics in physics becomes even more unreasonable because it turns out that like the reality itself is going to be something that can't be exactly mathematically modeled. And that's a problem, it sounds like you would say, for any theory that has vagueness about what the laws are.
Right. Yeah. So it might be a consideration, maybe not decisive one. Yeah. I entertain this possibility in my other paper, Fundamental Normative Vagueness. And in that paper, I say that it is a divisible consideration that can be balanced with other considerations, simplicity and explanation and unification and so on. So it might be the case that if the world is really governed by a pure state, that's the best we can do. And it's not completely hopeless. We can still model without complete faithfulness using mathematics. And we can extract lots of predictions from that. It's just that we cannot say anymore that mathematics is a perfect language of the world or the theory.
Yeah, good. I mean, so I wonder if the defender of the wave function view here could say something like, well, I mean, of course, this is taking on a substantive commitment in another area of philosophy, but they might say like, I'm an epistemicist. You know, like they
good.
They could be like, you know, I'm a Williamsonian believer in the wave function, right? Would that, I mean, that would solve the problem, I imagine, but then might be unattractive because you're taking on this kind of extra presupposition.
I think that's an excellent response. So I thought about this in my fundamental normative vagueness paper, which is that this arbitrariness can be given a precise categorization. I call this untraceability. So the precise boundary of the past hypothesis macro state for a classical stem or quantum stem is going to have this feature of untraceable law that has no resemblance to any other law we have in the history of physics. So for example, take Newtonian mechanics with Newton gravitation, and constant G, the value of constant G is precise and it's somewhat arbitrary, right? Given some unit system, it's not say a natural Remember, it is a
Right, it's not
complicated
one.
and precise. It's not. You can set it to one, but we know that given
yeah, right.
yeah, it's not really. So it's going to have some arbitrary features. But the arbitrariness is not untraceable. It's traceable. Think about perturbing the value of G slightly. Then suddenly most worlds compatible with the original version of Newtonian mechanics is no longer possible.
Mm-hmm. Yeah.
Now think about the path hypothesis as a law, perturbing the precise boundary of pH a little bit. It's not going to have this feature. Most worlds compatible with the path hypothesis still going to be possible, given this perturbation of the slight boundary. That's the sense in which the precision of what I call the strong path hypothesis, the precise path hypothesis, is arbitrary in a bad way. It's untraceably arbitrary, unlike any other constant or law in the history of physics. Huh. So I say this is a defeasible consideration again, not decisive, but it's interesting, right? That we all only accepted precise but traceable constants, traceable laws before. That's why we say, of course, the equation is not f equals ma to the power of 1 over 0.001. It's f equals ma, the simplest formulation. But also because it's traceable. We can have evidence, we can have observation to nail down this law.
Oh yeah, okay, cool. Right. So I mean, kind of a relationship here, just with the idea that like it's a bad feature of a theory if some of its parameters aren't measurable, you know, in principle or something, right? Yeah, good.
Yeah, so I'm sympathetic to that worry too, but I think that I want to defend the principle without appealing to epistemic resources.
Yeah.
So I think in some cases it's okay to have undetectable features if you keep the simpler theory. But once you have a simpler theory, on the other hand, that also dispenses with undetectability, that's even better.
Yeah.
So
well,
in this case, yeah. Mm-hmm.
Good, yeah, and I mean, you might say it's a little different having undetectable features of reality versus having undetectable parameters or constants in the laws or something like that, right? The latter might look worse than the former.
Yeah. Mm-hmm. So that's why there's a dilemma for the path hypothesis paper with wave function. Either we have untraceably precise arbitrary feature in the law, or we have fundamental nomic vagueness.
Oh, this is great stuff. I got to read this nomic vagueness paper.
Thanks.
All right.
Yeah, so that's one of the upshots of this paper. I realized I didn't really explain this well in this paper. So people have pushed me on this point, and I realized I need to say more. And it's interesting that the one calculus has this feature that it gets rid of nomic vagueness without introducing this this bad feature of arbitrariness. So the precise initial density matrix is precise, so not vague. But at the same time, it is not arbitrary in a bad way. Twinkling, perturbing the value of W0 is going to make a difference to how the world evolves.
Good. I mean, this gets to one of the questions that I kind of had in mind to ask you in my notes about the kind of Wentaculus view, right? So I wonder if, I mean, I guess a way to put the question would be, say more about why it isn't arbitrary, because like one might think it is in a way arbitrary to set the cutoff for how low entropy an initial state has to be in order to satisfy the past hypothesis for the capital P and capital H, right? Like the idea that there are some states that are kind of so let me put it this way. I'll put it to you this way. So the purpose of the past hypothesis in the theory is to explain the era of time. And it seems like it would be a little surprising if there was some precise line on the kind of continuum of possible initial entropies, such that entropies, initial entropies below that line explain the era of time, but initial entropies above that line weren't sufficient to explain the era of time. So say more about why it's not arbitrary.
Yeah, good. From that perspective, I think it's going to look a bit arbitrary why any postulate is going to satisfy the optimal trade-off between simplicity and strength, explanation, unification, and so on. And in terms of explaining the patterns themselves are a bit vague, right? Is that with a typical ice in a cup of water is going to melt, and there could be some exception somewhere in the universe, doesn't really matter, or somewhere in the universe history doesn't really matter. But somehow, if we get a precise law in the end, that's going to be surprising. That is, Higgs random doesn't match a command. So I want to say the intuition is roughly right, but the one calculus picture doesn't operate by starting from the partition, get into the density matrix. It's like the Wittgensteinian ladder, we kick away in the end. So the way we refer to that initial density matrix law is by constructing, in the usual Boltzmannian way, a macro state distinction, and using macro variables to kind of coarse grain things in space and give you a low-entropy state. But once you have that vague region in the end, we say there is some specification that's the one span, say, extended by the initial density matrix. They can forget about the partition and say that's the law. And whichever subspace spanned by the density matrix is the true subspace, the true density matrix for the theory. And why do we choose this theory over other theories? Well, I guess by super empirical virtues, maybe empirical ones too, in terms of explanations, simplicity, and others, that a slightly different one might not capture the input data as well as this one. So there could be some very hard to detect, but say cosmological patterns that is more confirmed on this theory than the other one.
Well, and it seems like, you know, it might be completely reasonable to be uncertain a bit where exactly the cutoff is. But it sounds like the view is for the laws of quantum mechanics, the way you understand it, to work the way that they do, there's some precise cutoff. And we might have some degree of uncertainty about what what the precise, essentially, like essentially there's a kind of constant in the laws of the theory.
That's right.
Right.
That's right.
And you know, we might be uncertain about exactly what the theory is in the sense of exactly what's the constant, just like we're uncertain about like what's the exact, you know, electron mass or something up to like X number of significant figures or something.
Yes. I think of exactly like this way you suggested, as a constant nature in the law, or something similar to constant nature. Although I think in the usual kind of way, think about constants, G and others, you can do certain kind of tabletop experiments or localized experiments to test the value. That's not the case for the path hypothesis. It's more global flavor to that. And there's no localized experiment we can do to test the value, the boundary of the initial density matrix.
I mean, in a sense, there sort of is, right? Because like, you know, it's like, for example, I know that constant, you know, think of that constant as representing like, you know, what's the kind of the minimum level of entropy that the universe basically can be expected to ever have in its history or something. Like I can kind of test that by you know, melting some ice and noticing that, you know, it was possible to melt ice, which it wouldn't have been if that constant was like, you know, high enough that like that level of departure of equilibrium was impossible or something. It's kind of it's like a fairly trivial and uninteresting test that we kind of knew the answer to a long time ago, but
it can narrow down the ranges of possible values of the initial state, but it's going to give you a coarse grained description of that in terms of entropy. Suppose there's a precise real number entropy. Even then, the number does not correspond to a precise set of microstates, say set of wave functions. That's the other source of vagueness, is the correspondence between precise macro variables, value variables, to the set of microstates. There can still be some fuzziness in the connection here. That's why in the original Mann-Calculus picture, I can grant them the weak path hypothesis with all the precise values of the macro variables, but not so much the strong path hypothesis that pins down the precise macro space in Hilbert space. That's the harder job, I think.
Oh, you were going to say, that just reminded me, you were going to say a bit about the nomenclature, the origin of the expression wentaculus
Oh
as
yeah,
opposed to mentaculus, right? Yeah,
right.
go ahead and do that. I mean, I'm sure.
Yeah, yeah. For
Yeah.
people who know about the mentaculus, it's basically simple change of word of M to W, where W is the symbol I use for when the density matrix. But for people who don't know the mentaculus, I guess the story is something like this: that so Bear Lower and David Albert had this picture for the architecture of fundamental physical theory that includes not only dynamical equations like Schrodinger equation, but also boundary condition laws, the path hypothesis, but also a probability distribution over states compatible with the path hypothesis. They call it statistical postulate. Together, you see that for deterministic theories, they entail probability distribution for every macro state at any time, so that you can have any proposition about the world. Say the probability that the next presidential elections won by so-and-so is 0.2, that can have a precise number attached by the theory. And they call this the probability map of the whole world, very much similar to a fictional story by the Coen brother movie, A Serious Man, in which it's a kind of a baseman who has a notebook with a probability map of the whole world, and they call this notebook the mentaculus. So the theory for them is called the mentaculus. For me, I call this the wentaculus. The difference, though, however, is that I don't need to postulate this fundamental statistical distribution over all possible initial quantum states. It's given to you by the density matrix, but something not in additional to density matrix.
Yeah, right. So it's kind of like part of, yeah. Right. The kind of like gnomic ontology or something kind of
Right.
includes
Yeah.
the effective like probability map of the universe,
right.
along with everything else.
That's right.
Okay, great. So, awesome. So is it open season for the other questions that I had in mind then for you about the paper?
Yes, of course.
All right, wonderful, wonderful. Yeah. So the first one that I was thinking of, is, when I think of like interpreting quantum mechanics in terms of density operators, the first thing that pops into mind is David Wallace and Christopher Timpson's space-time state realism. So, and I imagine a lot of viewers will be familiar with that view, according to which, so the Wallace and Timpson view, for those unfamiliar, is that instead of thinking about the state as a wave function, we can generalize, put together a more general ontology for quantum theories, including quantum field theories, as well as ordinary quantum mechanics, by talking about the quantum state understood maybe as a density operator, or Noel Swanson has done some work about generalizing this further to the idea of the quantum state understood as an expectation value functional, like from algebraic quantum theory. But anyway, the idea is that there's a state that, as Wallace and Timpson think, could be represented well by a density matrix, assigned to every region of space-time. And then those things are like a physical field, right? Essentially, quantum theory is the theory of a physical field that is density operator valued and assigns a density operator to every region, as opposed to like most fields that assign values to points. This one assigns values to regions. Yeah. So I think like a lot of viewers, including myself, would be curious, what do you see as the relationship between your wentaculus picture of a density matrix based ontology for quantum theory and this Wallace and Timpson space-time state realism picture?
Yeah, great question. So Wallace and Timpson, so to start from the similarities, I think that Wallace and Timpson and I agree that we can take density matrices, impure states in general, seriously as ontic, objective fundamental states, properties of space-time regions. So we all agree on that. And I think their proposal is compatible with density matrix realism and the wentaculus. But that we don't presuppose this particular feature that I have in mind. They don't select a particular initial density matrix of the universe. So for them, actually, I think they leave it open, whether the universal level, the quantum state, is pure or impure. Is it a pure wave function or impure density matrix? that's, I think, an open question on their view. So they don't presuppose that the quantum state of the universe has to be impure.
And they would probably see that as an initial condition rather than, you know, something that's a candidate for being a law the way you see it.
Right, right. And so my view is that primarily about the universal quantum state is objective and can be impure. And there's a particular choice of the impure state at T0. So the two can complement each other. But I would say that my view is more motivated by the arrow of time issue, and their view is more motivated by the quantum ontology issues. So just going to say more about their view too, that on the space-time state realism, you have a field-like structure in space-time, assigning properties to regions of space-time. But the field is not just valued at regions of space-time, but also it's not separable field. That is the state of the property of this big chunk is not a logical sum or sum of the regions of these two smaller chunks. And that's a departure from ordinary kind of fields too. And for the universal level, the whole space-time, the field is superly non-separable in the sense that you compose all the entangled regions in space-time. Yeah. So for some people who don't like fundamental entanglement or violation of narratability, as Albert called it, they might want to say, okay, can I understand the field as something more like a law of nature, governing how stuff is distributed in space-time? So you can say, in Schrodinger's first picture, it's a paper by Allori and co-authors, that you can have an aberrating picture in which the matter density distribution is given by the wave function. But the function, that matter density function is still separable in physical space-time. The quantum state places something like a law of nature. Again, if you have a density matrix picture, the whole universal quantum state then can become a law, simple enough to be a law.
Yeah, right. So, I mean, in a way, I would say, I guess that's kind of like, seems like the most major difference between your view and there. I mean, I guess there's kind of like two that might be equally major differences. One is, you know, you treat the state of the universe as like nomological, as opposed to a field that's kind of like a concrete thing that's taking on values in regions, right? And like the, you know, so on Wallace and Timpson's view, the density operators taking on values, you know, within the space of my head are the things that my head is made up out of in some sense, right? Whereas you wouldn't say any of the, you know, you wouldn't say the density operator that you're talking about is something that anything is made up out of. It's something that governs the evolution of the stuff that things are made up out of, right?
Yeah, that's my preferred way of thinking about the ontology here. But I have a subsection in the paper that's talking about the field interpretations, the initial density matrix. So you can think of the quantum state as concrete object in configuration space-time, but not R3n plus time, but R6n plus time. So it's going to take two values in each point configuration space. So it's going to be R6n with time. Or you can think of this as a multi-field on physical space-time, kind of following the revival of the multi-field picture that discussed by Gordon Bellot paper. And they can think of the quantum state as assigning a complex number, in the simplest case, to every two region of space-time. And each region made out of n points, and the number of particles. So that's still a possible way of thinking about density matrix. It's not the only way. And I just think of the multi-field and field interpretations as possible, but not the most natural interpretations of the density matrix. Once you are able to interpret it as a law, then why not? You can save all these apparent features of, say, compatibility with the Lorentz invariance, narratability, entanglement, no entanglement, and separability of the mosaic. Then everything becomes very nice and simple for the material ontology. It's the laws that are kind of entangled and all the strange things happening.
Yeah, super interesting. Right, and like it seems like so the classic objection to the nomological interpretation of the wave function is, well, come on, like the wave function is physically contingent. there's lots of other kind of like wave functions that could have described systems that were a bit different from the ones in the real world. But right, but it seems like you would cite as an advantage for your view that there isn't the same kind of contingency.
Yeah,
Density matrix.
the initial density matrix is going to have this nomological necessity as much as the past hypothesis does.
Yeah, good. So in contrast with, I mean, well, let's talk about it in Bohmian terms, because A, that's kind of your preference, and B, like I think it's kind of like the easiest way to understand it in a way.
Right. The single world picture, right?
Yeah, exactly. Right. So it's kind of like, let me see if I'm getting the kind of cosmological picture here, right?
Yeah.
So on a kind of like naive ordinary quantum mechanics Bohmianism with wave functions as the thing that guide the particles, you might say, well, the reason why like you know, there's like a fireplace in my room here instead of or like, you know, the reason why there's like a wood fireplace instead of a gas fireplace or something is because the wave function was one that would tend to guide the particles into the wood fireplace region of configuration space rather than the gas fireplace region. So on your view, if I understand it right, the state would just contain a huge number of kind of different I mean, maybe subsectors would be the right word, that if the particles had been set up initially differently, there could have been a different fireplace here, or there could have been like, you know, some kind of ocean here or something. And all of that contingency, as I understand it, those possibilities are still possibilities, but what makes them contingent isn't the initial state. What makes them contingently true, I should say, isn't the initial state guiding the particles into those configurations. It's, you know, the initial state allows all kinds of different ways things could be, whatever, you know, you might say it allows whatever ways things could be that would be consistent with the past hypothesis as you're understanding it.
That's right.
And it's just the initial distribution of the particles that.
That's right. The contingencies are all traced back to the initial particle configuration in the Bohmian Wentaculus.
Yeah.
You still have, I think, roughly the same number of possible worlds, same kind of possible worlds, same classes, because they are all agreeing on the same macro state.
Yeah.
Same possible macro state. It's just that the contingencies are not going to have two sources. In the Wentaculus picture, the two sources of contingencies, where particles was at T0 and what wave function was at T0.
Yeah, good. Yeah, I mean, I definitely like, you know, I see exactly why you think of it as a significant advance over classic Bohmian mechanics. You know, there's all kinds of, I mean, there's all kinds of things about classical, like, you know, like the Everett and denial objection to classic Bohmian mechanics, right? That this seems to evade in a way. I mean, I imagine they might still want to say something like, in some sense, the density operator for the universe contains substructures for what they might think of as like empty branches that would contain a gas fireplace in my room or something like that. And so they might still want to press that objection, but it makes it kind of less natural seeming, I guess.
Yeah. I think there are several problems with that objection about Bohm is ever in denial. But one of them is that the different ontology matters here. That is, Bohmians don't think of gas stoves and tables and chairs are made out of quantum states. They think of them made out of particles. But on this picture, there's additional reason for saying this. That is, the quantum state here is really a law. So there's no sense to be made that my table is made out of the quantum state. Unlike the Wentaculus picture, the quantum state might still be not a law and contingent, and somewhere like material stuff, like a field, as Albert and May and low, say, and that might give more support to the objection that Bohm is ever in denial.
Yeah. Yeah. Right. Right. Yeah. Maybe the way to put it is that it makes the view that the state is a law rather than a contingent physical thing more natural and palatable. And so
That's right.
in that
That's
sense,
right.
kind of helps to avoid the ever denial objection.
That's very helpful. I haven't thought about that. So yeah, maybe there's another paper to be written here.
Cool stuff. So one of the things that's kind of that we've just been foregrounding a bit is the Bohmian aspect of this picture, right? So you discuss Everettian and collapse interpretation, GRW versions of the Wentaculus picture, but it's clear that your heart is more in it with Bohmianism, and you kind of settle on what you call W Bohmian mechanics for the second half of the paper. And in general, like it's fair to say from your whole body of work that you favor the Bohmian mechanics version of the view over the alternatives. Now, is this for just kind of general reasons about you thinking the Bohmian mechanics is the best interpretation of quantum mechanics in the first place, or do you think that the Wentaculus density operator ontology view gives additional reasons to favor Bohmian mechanics over the other interpretations?
Yeah, so in the paper, try to be as ecumenical as possible, but I'm probably showing off my prejudice already. That is, I focus more on the Bohmian picture, and in the last section, talk more about the W Bohmian mechanics theory. I think of, so I used to be very attracted to Everett until I read papers by you and Kent on the circularity objection to probability issue in both Everett, and also Albert's objection and other people's objection about justifying the Born rule. So I'm, worried about the probability issue in Everett not being even in principle solvable, but I still hold up some hope that it can. So I assign a non-zero credence to Everett. So I don't rule it out, but I find GRW and Bohm more natural and promising in the sense that there seems to be theories that at least in principle, I can see how to give an analysis of observations and probabilities in a non-circular way and in a non-question begging way. So that's why I am a bigger fan of Bohm and GRW than Everett. However, in the paper, I try to be ecumenical, and in my later works, I also try to show that the Wentaculus brings out different aspects of Bohm, GRW, and Everett. So for the Bohmian version, it does make the theory more compelling, and Wentaculus makes Bohm more easy to understand, I think. Right. So we talked already, the normal loss interpretation of Bohmian mechanics is a very natural one, that you have particles that move or fields that undulate in space-time. And it's the quantum state that guide how they move, how they behave. Now, the guiding talk already suggests this nomological character. It's not like there's back reaction from the particles or fields to the quantum state. It's like one-way direction. This tells us how to move, and there's no back reaction. So already you have this nomological character built in, but the simplicity of the Wentaculus picture says, well, you are now justified in taking the quantum state to be your law, telling how matter how to move. So in this case, it removes one of my deep worries about Bohmian interpretation, that do I have to be a high dimensional space realist? Do I have to be a field realist? In the case of Bohm 2, there's another feature that I think is worth mentioning. One of the questions you mentioned in your email is that the unity of the universe and the subsystem was dramatically increased when we go from wave function to density matrix. Already in the wavefront picture, for the universe, the particle dynamics obeys gradient of psi. But for particles with spin, the subsystems, because of entanglement with the environment, it's not going to obey something like gradient of the effective wave function. There's only the effective density matrix for particles with spin. And in that case, the equation for the subsystem is going to look different from the equation for the universe. And that might be a feature we can consider. once you have a density matrix picture, both the universe and most subsystems in the universe are going to be guided by gradient of the density matrix. Different density matrices though.
Yeah, good. Okay. So there's a kind of like, right. I mean, what I was reminded by that part of the paper was this kind of move that Wallace has made in some recent work. Like he kind of, I think he kind of sees this as a criticism. He mentions about Barber's relational mechanics that, you know, a feature of it that it doesn't share with ordinary Newtonian mechanics is that, you know, in Barber's mechanics, you can't use the same, you can't model subsystems of the universe the same way you model total universes.
Yeah,
right?
yeah.
Because you have to kind of like include for the subsystems some assumptions about what the kind of like you know, what the rest frame of all the other matter that's not being modeled is, whereas that's not true for the whole universe. So yeah, right. Yeah,
and it's also in people like pragmatic humanism who have written about this, which I think is kind of interesting insight, even for non-humans. They say that one consideration for laws in the best system is that they can be applied to quasi-isolated subsystems. It's kind of Michael Hicks' dynamic humanism, that it's not just as simple and informative, but informative in the sense that they can be applied to almost isolated subsystems of the universe.
Yeah, good. Yeah, I hadn't thought of that parallel with the Mike Hicks stuff. That's cool.
Yeah, but at the same time, you see this tension that I sometimes feel too. There is fundamental laws only at the level of universal level. So it is not a surprise, perhaps, that it's only when you have the universe as a whole, you have a complete description of the physical state.
Yeah.
So it'd be an interesting feature, but not required for someone who says there is fundamental law that govern the universe as a whole. So I feel the pull on the other side too. So it's not decisive. It depends on prior commitments on how laws should govern or how laws should describe.
Yeah, that's right. And you know, in Wallace's case, it seems like the pull of this kind of argument goes along with a commitment to the idea that it's usually or always a mistake to think of physics as modeling the entire universe.
That's right.
Which, you know, that's I mean, by philosophy of physics standards is a fairly radical view, and I don't think one that you or I would necessarily go in for. I mean, like speaking for myself, but I think you and I probably have the same kind of orientation.
I think I'm with you on that one. But I think there is something to be said about the methodological principle that physicists themselves are employing. They're trying to build effective systems, effective dynamics first, and then extrapolate when we refer to the universal dynamics. So it'd be nice if realists like us can give an answer to why we have this methodological preference, and does that figure into metaphysical laws too? So I think non-humans should not be ashamed to borrow the insights of human friends who say that there are lots of defeasible guides to for them would be constitutive rules for laws, but for us, defeasible guides for the true laws. And maybe it's one of them, unity of the subsystem and the universe.
Yeah, I totally agree. I think, like, you know, the question is less whether these principles are good principles, but whether they're principles that are in some sense kind of, like you say, constitutive, analytic, like whatever, metaphysical principles, versus are they like methodological, epistemological principles about like what we should expect the laws to be like.
Just going back to the earlier question you asked me, sorry, long-winded way of replying. So in the Bowman case, I think the Wang calculus makes Bowman mechanics more natural and more compelling. And for the Everett case too, there is some sense Everett becomes much stronger on Wang calculus than on the Wang calculus. Here's what I mean. So with a new preprint on this, it's called strong determinism. That is, usually we think of laws having informative features like determinism, that is fixed in the state at one time, then fix the entire universe back and future. But you can have a stronger kind of determinism, or strong determinism, that says the laws fix the entire universe all at once or give you only one possible history, nomologically possible history of the entire universe. And that's what happens with the aberrated version of the one-takeless. Because there's the exact choice, nomologically exact choice of the initial condition and exact dynamical law, deterministic dynamical law. So there's only one possible history of the multiverse. So average one-takeless, I think, is the first example that satisfies strong determinism for any realistic physical theory. Setting aside, of course, the probability worries that you and Kent raised and other people raised. That is, if those problems can be solved, then this theory will be empirically adequate and strongly deterministic. Might be the only strongly deterministic theory we have for any realistic views. And now, if that theory is empirically equivalent to, say, the Bohmian one-takeless, Bohmian man-takeless, there's a sense in which we cannot find out whether our theory, our world, is strongly deterministic or not. Whether we're always governed by strong determinism or pure determinism or indeterminism. There's empirical equivalence of all those theories. So that's something I think that hasn't been emphasized much in the literature. But it's a kind of cool feature of Everett that allows this possibility.
Yeah, you know who might like that consequence of it? I don't know if you've ever talked about it, but is Al Wilson.
Yeah, I have.
Yeah, right. Because he has this view where like the semantics for ordinary modal ideas, like I, could have had eggs for breakfast today or something, comes from the fact that there are like Everettian worlds where I have eggs for breakfast.
That's right.
Yeah,
so it's kind of very natural for Everettian modal realism, as Wilson defends it. Yeah. And I think it provides an improvement too. For Wilson's view, at least from the view I got from the book, that he wants to say Everettian branches provide all the contingencies there are. But of course, we can vary the initial wave function on standard Everettian quantum mechanics, such that there will be additional contingents not encoded in any branches, at least in this multiverse. In that case, the theory is missing some contingency or some possible world. But for the Everettian one-takeless, there isn't anymore. It is the only nomologically possible world, so there's no nomological variation of the initial condition. So it provides kind of improvement for the foundations of Wilson's view.
Yeah, well, and a thing I didn't used to realize about Al's view is that I guess that he's a necessitarian about laws. So I suppose it would entail that there's only one metaphysically possible quantum state. Although, like there's the sense of metaphysical possibility that applies to the quantum state, and then for him the sense of metaphysical possibility that applies to alternative branches we could have been in, essentially.
That's right. So in his book version, he says he at least conjectures or hopes that cosmology might pin down a precise pure state of the universe. What I say in response in the paper version, at least, is that he need not make that assumption. He can say, well, if the one-takeless is true, there's no more conjecture to be made. The theory is true, then there's only one nomologically possible world.
Yeah, right. Yeah, yeah, that's interesting. Definitely an appealing combination potentially. Yeah, good. So let's talk more about this stuff about laws. This is kind of the last big point that I wanted to ask you about. So it sounds like you, like myself, have a kind of preference in favor of non-Humean governing law pictures. And a thing that I've always thought about the past hypothesis is it's not an especially good candidate for a governing law, because it's kind of like, it's this thing that like it seems to be about initial conditions, right? It's kind of like about like what sort of initial conditions should we expect to hold, and it's not about dynamics and like the evolution of the past into the future, the kind of thing that like Maudlin, for example, thinks. I don't agree with Maudlin that this is kind of necessary to the idea of what governing laws are like, but like it is intuitive to think that governing laws will tend to be laws that tell you how the past turns into the future in some sense, or dynamical laws anyway, right?
Right.
So but you defended the idea that the past hypothesis in your version of it is well understood as a governing law. So like sell me on that idea.
I try, but I think your intuition is widely felt by many people, many anti-humans and humans alike, about the anti-human view that it cannot accommodate something like the past hypothesis. So I've been thinking about this too. So you know that I am anti-human, but I've been for many years hanging out with humans. So I've been working on trying to defend humanism to the best I can to really understand what's the key difference between my view and humanism.
Is Craig a human? I gotta ask.
Oh yeah, Craig is a human.
Okay, all right.
He's becoming, I think, so he is better by system account of laws. He co-authored with Jonathan Cohen is a version of the best system view of laws.
Oh, of course. I've read that paper. Of course he's a human. Sorry, go on.
Yeah. So I studied with humans and also non-humans. And I like humanism because I think it offers a lot of insights about laws that I often overlook as a non-human. And so when I reflect on non-humanism, I realize, back in grad school, I had this picture very close to what Tim Malton had in mind. The laws have to be fundamental laws of temporal evolution, governing how things change in time. Maybe not deterministic, but at least how things move or change in time. The future is made by the past and the present. The universe is made dynamically. And I realized I don't really understand that picture anymore. And I realized also that the core of anti-humanism doesn't presuppose that laws have to be or tend to be those forms. For example, even the Einstein field equation by itself does not have this form, even though it can be decomposed with some costs and some throwing away solutions to be a Hamiltonian formulation, but it doesn't have to be. That can we non-humans say the Einstein equation can be by itself a fundamental law of nature that governs the universe? I think yes, right? Similarly for Gauss' law, describing how matter distribution in charges in physical spacetime, and it's not about time evolution either. Lots of constraint laws are of this form, although they apply to all spacetime in some way, general, not particular. The past hypothesis is a special case of constraint laws that constrain the universe such that it has a special boundary. But what about the initial state that prevents it from being a fundamental law? And I realized maybe it's tied to our notion of the arrow of time, that the initial one is the beginning, in some sense, the past, or a T0. So we think it's always contingent about T0. But usually it's because we don't have a good candidate for characterizing that state. In Newtonian mechanics, before thinking about the past hypothesis, we say you can freely vary, the initial state, but not exactly, because we don't have free variations to anti-entropic ones, right? Or we don't have free variation to such that it is completely chaotic. So there must be some constraint we implicit putting anyways. It's just not explicit. So Sheldon Goldston and I have developed and defended this view called minimal primitivism. That's similar to Tim Malton's view, in which laws are non-human. They're not just summaries of mosaic, but they are governing. But they govern by constraints. That's why it's minimal. They don't presuppose a fundamental direction of time. They presuppose that laws have to be dynamical evolution laws. They can be any form. But how to identify laws or discover them? Epistemic guides, simplicity, informativeness, elegance, explanation, unification, all of those features are diffusible guides for us to helping us to discover the laws, the fundamental governing principles of the world. So in this picture, there's no metaphysical prohibition against having the past hypothesis being a law, or the Einstein field equation being a law, or Gauss law being a law. They can all be laws, but our reason for preferring to be laws are going to be judged on epistemic grounds. And that's why I think once we realize, in part is kind of connected to how we think laws explain. There is some difficulty I have even with simple articles I made. How does that govern, right? It's not like there's a slice of time such that it contains all the seeds of producing the future. That picture is wrong because we know, we accept usually that velocities, momentum are not grounded in any slice of time. it's going to be grounded of features of particle position over some period. And that means there's no privileged time in which they can produce all other times. So already governing laws explain not by producing things from each slice of time to next slice. It's going to be some like a block of space-time, not a block
a neighborhood of a slice or
a
something.
neighborhood of space-time.
Perhaps.
That becomes less natural already than the intuitive laws we have.
Yeah.
Moreover, if you have a four-dimensional space-time picture, block universe, nothing's really, dynamically changing the whole space-time. There's no making of the universe. There's no becoming as kind of objective. So this talk of production becomes even more mysterious for me when I think about the block universe. So the core of non-humanism, we argue, is the idea that laws governed by limiting or telling us what's physically possible, what's physically impossible, for the simplest case. And the past hypothesis tells us what's possible, right? The possible ones start from a low entropy initial condition. What's impossible is those that start from the high entropy initial condition.
Mm-hmm.
So it plays the same role as other governing laws. And the reason we infer it as a law is because its role it plays in the other parts of theory, namely grounding the asymmetries of time, grounding second law of thermodynamics, and giving us a nice amount of counterfactuals and so on. And moreover, it is simple. The simple postulate of initial condition that can give you a lot of explanation for later parts of the universe. That's what makes it a good candidate for a law of nature in our picture.
Now, does your view of laws have the kinds of consequences for like counterfactuals that like Mark Lang's view does, for example? Like, is it within that kind of a picture where it's like which I think is shared by Maudlin's view, although in other ways it's very different from Lang's view. But this idea that that if you have a counterfactual whose antecedent is compatible with the laws, then the consequent is going to be compatible with the laws. Is that?
Yeah, there is this idea of stability of counterfactuals that we can make to infer what the laws are. But I think for Lang, the proposal is more radical in the sense that it's counterfactuals all the way down.
Yeah.
So it's like counterfactuals grounding the laws, not the other way around. For Tim and for us, I think we want to say, if they're counterfactual facts or facts for counterfactual, they're grounded in the laws. It's like we can give a semantic for counterfactual in terms of fundamental laws of nature.
Yeah.
But they're all related in the sense that you can give a semantics for counterfactuals in terms of laws or vice versa.
But good, like, yeah, and I think that's appealing. Like, I think it's a little odd that the Lang view kind of puts things with the counterfactuals first. Do you think that, I mean, is it, I guess the question I was wondering though is if you do think that the stability part is going to be a feature of the account, because the reason I ask, I guess, is like von Frossen had this old point against like the Armstrong type view of laws as necessary connections between universals with something like, what do you mean necessary? Like what is it that makes the relation that you are appealing to between possibilities? What is it that makes it physical possibility and not just some other kind of like, holding X fixed for some X type of possibility that we can think of all the time? And I mean, the nice thing about Lang is that he has an answer to that, which is, physical necessity is the type of necessity that goes along with stability under counterfactuals, whereas like, the necessity of all the things that are possible holding fixed, the color of your shirt or something like that are not going to exhibit stability. So I guess that's kind of like where the question is coming from.
Yeah, that's a nice feature of Lang's view. And I've been thinking about this recently too. And I think even a primitivist who think the laws are fundamental facts that govern can appeal to stability as a criterion, a defeasible criterion for inferring what the laws are. That is, we might want to have a picture in which primitives are, in the metaphysical sense, giving rise to grounding all those modal notions, counterfactuals, possibility, probability, and so on. But in some way, we can infer what the laws are by seeing how we use those modal notions in practice. It can be a kind of evidence for what laws we mean to be fundamental anyways. But you see, this has to be defeasible in some sense, because my view, at least, in the paper from Determinism, I show that everything one calculus is only deterministic. It is at least possible, metaphysically possible, for there to be a theory such that the nomological possibility is exactly, there's only one possibility, and that will not be counterfactually stable for non-trivial counterfactuals, which means that if that is a possibility, then stability on a counterfactual variation must be the feasible guide, not the necessary condition. So it is something like epistemic guide again. It's not a metaphysical principle imposed on all theories. Otherwise, you say it is impossible for that to be a strongly determinate world or strongly determinate theory. That seems too strong to me, and that seems to be legislating too much. And the metaphysics should not rule out this possibility.
Got you. Okay, so then, yeah, that makes perfect sense, and is a nice kind of full circle with the stuff we were just talking about. So then, what do you think is distinctive about physical modality? Like, what is it that makes physical possibility like a kind of like a more robust sort of possibility than, you know, like define like headset possibility to be possibility, the, you know, which states of the world are possible consistent with the existence of my like little headset, right?
I see. Yeah, it's a great question. I haven't thought much about it, but here's my flat-footed answer. So in the everything case we talked about before, determinism, everything one calculus, there's no non-trivial counterfactual for the whole multiverse, but there can be counterfactual about branches of multiverse. Say this particular history, this particular decoherent history. So we can make sense of non-fundamental counterfactuals that still have this stability feature. They're all invariant under, sorry, the laws are invariant under counterfactual variations. So the initial projection give rise to all these different counterfactual histories, counterfactual in the sense of different branches, not different universe, different worlds. So in that case, we might still use Land's criterion to give us answer for why physical laws are more robust and more stable, more elite, right? But you have realized that the criterion is not a metaphysical principle anymore. It's more like epistemic guide.
Yeah, right. Yeah, good.
And it depends on how we
point.
catch out counterfactuals for average. And I know you are interested in this question too. How should we think about action and, you know, decision and possibilities and counterfactuals in average? It's just kind of a hard question, right? Once you have branching, do I think of me acting on the future as being responsible for this branch or that branch or all the branches? And that seems too much to ask. So we have to have some fine-grained notion of possibility here than all the branches.
Yeah, good. Okay, interesting. I mean, your answer seems like another place where Everettianism is kind of congenial to like the Al Wilson view again, right? So
right, yeah,
yeah. All right, great. Well, yeah, lots of awesome stuff that's come up. Really interesting discussion, Eddy. I think I'm ready to ask my kind of closing questions for you.
Yeah.
So yeah, so at the end of these, I always ask these two questions. So the first one being, I'll put it this way, kind of, how has your thinking about this topic? I mean, of course, in your case, you have like a big body of literature following on from this topic, right? So like, what's an important way or some important ways that you feel like your thinking about this topic has evolved since then? Like, how do you, like, maybe especially, how do you look back on this paper, and is there anything you feel like you wish you had said differently or in addition to what's in there?
Yeah, so I wrote this paper in graduate school in 2017. So it's been almost 5 years, and it was accepted in BJPS 2018. It was published in print finally last year. And so over the years, I've been thinking, well, there's always this nagging question. I didn't answer this question in a complete way, and I didn't say carefully enough. So that's why I wrote other papers to try to, first of all, to clarify things, more illuminating way, but also trying to flesh out what I really think about the subject. For example, the uniqueness of the initial projection. What do I mean by unique? So I wrote this paper on normative vagueness to clarify, okay, here's a real issue here about normative vagueness, but it can actually be solved in some way by the one calculus, but it wasn't clear in the original paper. There's also the question, how does this help humans? Think about human supervenience to get rid of the entanglement from the mosaic. And I have two paragraphs or one section on that in the paper, but another paper is published this year in News about how humans can give a unified account of time asymmetry and entanglement in a best system, such that the mosaic becomes completely precise, separable, narratable, and in some way simple. And the best system becomes non-vague, and it can be at least Lorentz invariant for every case, and so on. So those questions were things that which I said better in the original paper, but I was happy that I could say them more in other papers, elaborate them in different articles. And I don't say much about my philosophy of science, of what I mean by laws of nature, how that connects to counterfactuals, explanation, understanding, and constraints. So I say more in this paper with Sheldon Goldstein, and write a new book on laws of physics for the Cambridge elements, trying to tie up these ideas in a more fuller book treatment. Yeah, so I've been basically writing follow-up papers to this paper, which in some ways a kind of nagging question I didn't really solve in the original paper.
Good. Yeah. So in a way, the right answer is check these out. Right? Here's
right.
Good. And you know, as I guess kind of another nod to follow-ups or other projects. Final question. You know, is there something that you're working on now, or you know, kind of like is in the pipeline now that you'd like to you know, draw the viewer's attention to?
Yeah, thanks. So I finished a preprint on strong determinism. So it's elaboration definition of this idea applying to the aberration one calculus. And I'm writing a new paper on the simplicity of physical laws that try to say, okay, for us non-humans, what does simplicity mean? And what role can it play in our theory of laws? Is it metaphysical? It's epistemic? And if it's epistemic, then is it justified? And I say that it is justified because it's basic belief, properly basic postulate in the theory that cannot justify further. And I try to apply that to the case of the past hypothesis and other things that to say that non-humans want to realize simplicity being absolute guide can have the same freedom to contemplate a wide variety of laws that humans do. And this gives us the freedom and also principal choice criterion for choosing what theories to put in governing laws. That's why even though we say the past hypothesis can be governing law, I don't say all initial conditions can be a governing law. There must be some criterion of simplicity we use to choose what laws to consider or favor.
Yeah, although presumably you would say that it's not impossible for all the initial conditions to be a law, but right. it's just extremely implausible that they should be.
Implausible, right. Or in the Bayesian term, unlikely.
Yeah, exactly.
Giving you the priors. Something we have to say in the end, because we have to solve problem induction, and we know that cannot be solved without backing the question. So I'm going to back the question and to say, here's the fundamental epistemic norm we all should adhere to. Right, but it's not in terms of impossibility, it's in terms of probability.
You really are a man after my own heart, Eddy. Except, I mean, like I'm not a Bohemian, but I'm not a Bohemian, but in terms of like philosophical methodology, we're very we're very in sync. Which
thank you. I'm glad to hear that.
Yeah. I mean, awesome. Thank you for making another episode of this. You know, super fun for me anyway. I really enjoyed this discussion.
I enjoy it too. Thank you so much for having me. It's very helpful to me. I had so many good comments and questions from me. I need to think about 2 other papers I can write. So.
Yeah, well, it's very clarifying for me too to understand a view that was already pretty interesting to me. So thanks so much for coming on, Eddy.
Thank you, Dave. Thank you so much.